By the close of the 19th century, physicists worked under a single unifying certainty. Light was a continuous electromagnetic wave. While Max Planck had recently suggested that matter might exchange energy in discrete amounts, light itself was still governed by James Clerk Maxwell's wave equations. In the late 1880s, Heinrich Hertz set out to provide the first physical proof that Maxwell's invisible radio waves actually existed. His setup was straightforward. A high-voltage transmitter produced a spark, launching electromagnetic waves across the room toward a separate metal loop acting as a receiver. The experiment was a success. When the transmitter sparked, a tiny corresponding spark appeared in the receiver. Maxwell's theory had been physically confirmed. However, Hertz noticed something he hadn't planned for. The tiny receiver spark was easier to produce whenever ultraviolet light from the transmitter happened to shine directly on the gap. Ultraviolet light was somehow interacting with the electrical state of the metal. He ran a quick control test. He placed a pane of glass in the way to block the ultraviolet rays, and the enhanced sparking stopped immediately. Hertz recorded the observation as a curious side effect. Having achieved his main goal of proving Maxwell right, he did not pursue it further. The problem for any scientist following Hertz was the environment itself. In a room crowded with high-voltage coils and radio waves, it was impossible to isolate the specific interaction between light and metal. To understand what was happening, the experiment had to be stripped of its complexity until only the light and the metal remained. Wilhelm Hallwachs attempted to isolate the effect by removing the radio waves and sparks entirely, testing if ultraviolet light alone could change the electrical state of a metal plate. He reduced the experiment to 3 elements: a polished zinc plate, a source of ultraviolet light, and a gold leaf electroscope. The electroscope was a standard tool of the era, used to turn invisible electric charge into visible physical motion. When the metal plate is charged, electricity flows into 2 extremely thin gold leaves. Because like charges repel, the leaves swing away from one another, forming a visible V shape. This provided a clear indicator. If the leaves remained apart, the charge was held. If they collapsed, it was losing charge. Hallwachs gave the zinc plate a negative charge. The gold leaves held their position. But as soon as ultraviolet light struck the plate, the leaves collapsed. The negative charges vanished. But when filled with positive charge and hit with the same beam, the leaves stayed parted. It only ejected negative charges. Physicists now knew that ultraviolet waves could physically eject negative charges, electrons, out of metallic surfaces. But the electroscope couldn't tell them where those electrons were going or how much energy they carried away. In 1902, Philipp Lenard sent it to capture those escaping electrons and measure their exact properties. This schematic shows the custom apparatus he built to do it. It's a glass vacuum tube where ultraviolet light enters through a quartz window, strikes a metal plate, and releases electrons which travel across the empty space to a collector. According to wave theory, turning up the brightness of the beam should simply push the electrons harder. A more intense wave carries a larger electric field, which should impart greater force, and therefore greater energy, to the electrons it knocks loose. Lenard applied a retarding voltage, an invisible wall of resistance, until the escaping electrons stopped and turned around, recording the stopping voltage. He then cranked the light to maximum brightness, releasing a massive flood of electrons. Yet they hit that exact same invisible wall. The stopping voltage hadn't changed. The voltage required to stop every single particle was a precise measurement of their maximum kinetic energy. This graph represents the conflict. The first curve shows the result for dim ultraviolet light, with the current dropping to 0 at the stopping voltage. Maxwell's wave theory required that a brighter light, a wave with more amplitude, would exert a stronger force, hitting the particles harder and giving them significantly more energy. Yet when Lenard increased the brightness, the data showed something else. The curve started much higher on the vertical axis, but it returned to 0 at the exact same point as the dim light. Brighter light successfully released more electrons, but it did not give any individual electron more energy. Lenard's data directly contradicted Maxwell's foundational laws. A wave with massive amplitude should have battered those particles with far more energy than a dim, weak wave. Lenard tried to rationalize the result. Because the intensity of the light didn't alter the energy of the electrons, he assumed that the energy was already stored inside the atoms of the metal. He treated the light as a mere trigger. He had documented a profound mystery. The experimental data was clear, repeatable, and undeniable, but the existing theories provided no way to explain it. The result was a total impasse. The most successful physical theory of the 19th century had predicted one outcome, and the lab had produced its exact opposite. The data sat waiting until 3 years later, when Albert Einstein reviewed Lenard's notes and proposed a completely different definition for the physical nature of light itself.
Coming next, Episode 4, Einstein's boldest leap. How do you prove that light comes in pieces